Hey Elise, sorry it took me so long to get back to you with this second video, but I was sick for about a week or so. I'm not sure what it is, but I think it's dengue fever. Luckily, I didn't have to go to the hospital or see a doctor or anything. So I'm going to start off by answering a question that you asked me through email, and that question was, where does the idea of the dot product or scalar product come from? So I'm going to give you a relatively simple explanation. But so first, let's think about the the idea of having vectors as matrices. I'm not going to go into too much detail about that for now, but basically a matrix is it holds several numbers in there, as opposed to just one. Although a matrix also can be one. But in this case, we have two. We are concerned with two three-dimensional vectors. So there are 6 numbers in this matrix: 1, 2, 3, 4, 5, 6. And the idea of the dot product comes from this matrix idea called the norm. And the norm of a matrix is not a set defined mathematical function, but in general, it just means that you're taking one number that is somehow affected by all the numbers inside the matrix. So again, the norm is a function that takes the 6 or however many numbers inside a matrix and punches out one number. And the norm that physicists have found useful is something called the inner product space. And basically the inner product space just so happens that if you have vector A and vector B, the inner product space will give you the area of the parallelogram formed by those two vectors. So that's as simple of an answer as I can give you. So there's a second way of multiplying vectors though, and that's called the scalar product, because the result is a scalar. The scalar product is most often known as the cross product because that's the symbol you use. And so let's say, for instance, you want to take the cross product of two vectors, and let's say, for instance, that we have vector A cross vector B equals vector C. What does this mean? So let's say we have vector A and let's say we have vector B, right? Both arbitrary, pointing somewhere off into space. So whenever you have two vectors, you can form a plane in which both of those two vectors are going to lie in. So you can take a few minutes to prove that to yourself, but I'm going to proceed as though that's true. Although you can't form a plane if the two vectors are parallel. Well, I mean if they're the same vector. But any two vectors in space that are not collinear, you can form a plane through. So once we have a plane, the result of the cross product, so if this is A and this is B, the result of the cross product is going to stick straight out perpendicular to that plane. And there's only one direction in which C can be. There's only one direction that C can face so that it is perpendicular to the plane created by A and B. And the second question that is apparent is, let's say A and B are like this, and so the plane is parallel to the screen, in this case what you're looking at. So is C coming out at you or in towards me? And how we figure out what direction C is in is determined by the right-hand rule. So if this is A and this is B, you take your right hand, point your non-thumb fingers towards A, curl them towards B, and then the direction that your thumb is in is the direction of C. That's called the right-hand rule. You probably used it in in the first year of physics with Mr. Robinson, but this specific right-hand rule is applied to cross product. Note that if you have negative A times B, you will get the opposite direction. Or if you have B cross A, you will have the opposite direction. It's a little tricky. Unfortunately, I can't really describe it too much through a screen. But if you have any questions, please let me know, and I'll try to elaborate further. I'll try to find some helpful diagrams. So now we know the direction of vector C. The magnitude of vector C is equal to magnitude of A times magnitude of B times sine of theta. And theta, again, is the angle between A and B. Note this is very similar to the dot product, but it's sine instead of cosine. And yeah, that is all you need to know, but I'm going to go a little further again. Since I already talked about matrices before, I'm going to talk about matrices again. So where does this come from, since I know you're going to ask that? The cross product. So A and B, again, can be written as a matrix, which is like this. Again, you see you have I, J, K as your unit vectors, and AX, AY, AZ, BX, BY, BZ, right? And usually, you'll notice, matrices have those corners that look like that, right? But in this case, it's just a straight line with no they're absolute value signs and not brackets. So this actually isn't. So when you use that terminology, it indicates that expression is something called the determinant. Again, it's another tricky linear algebra term, but every matrix has a determinant, and it's determined through some very tricky theoretical stuff. But you can also find the cross product algebraically instead of doing absolute value of A times absolute value of B sine of theta, because that method only gives you the magnitude of C, and then you have to find the direction of C separately. This is difficult because it'd be a lot simpler if we just found out what Cx was, Cy was, and Cz was. So basically, the determinant of A cross B is this thing, which is AX I hat plus AY J hat plus AZ K hat. This is vector A cross this vector B. This turns into you distribute across the product, and so you have AX I hat cross BX I hat, BY J hat, and BZ K hat. And because these are our unit vectors that we're crossing, the cross product is a little simpler here, and we find out that I cross I is 0 because anything cross itself is always 0. You can prove this yourself using the fingers and the right-hand rule. AX I hat cross BY J hat is equal to AX BY K hat. You don't have to write this down, by the way. And I can't even read that. AZ J hat cross BZ K hat is equal to AX BZ minus J hat. All right, so that's very complicated, but you can write this down, which is AYBZ minus BYAZ I hat, aka CX, plus blah 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 blah. There is a mnemonic device that you can use though, which is that. Oh, I guess I should have told you this first. but this is just a mnemonic device, and so you know that, okay, Cx is based on, Cx points in the direction of I hat, correct? So let's cover up the I hat row, and then you have Ay Ay times Bz minus Az plus By. That's Cx. And then Cy is equal to Ax times Bz minus Az times Bx, whole thing negative. So the entire J term is negative of this times this minus this times this. Again, really complicated. I mean, I'm sorry, not really complicated, but if you do the math out, you'll see why the J term is negative. And then K, same thing. You have Ax times By minus Ay times Bx. Alright, so that's the cross product is kind of difficult to understand at first, but keep in mind, again, there are two ways of doing it. The first way is find direction and magnitude, you know, using direction where C is perpendicular to both B and A, and in or out determined by the right-hand rule. And magnitude is AB sine theta, and the second way is actually what I prefer, which is to look at, arrange this out in so it looks like you're finding the determinant, and then you cover each one. Cover each one, and then use your eye to this times this, oh shit, minus this times this. As an additional suggestion to this video, the Wikipedia article for the cross product is very informative in defining the cross product and telling you how to solve for the cross product. So I would highly recommend you looking at that, since I can't really, it's very difficult for me to smoothly enunciate what I'm trying to say through paper. So with that, I'll promise to you I'm going to get the next video to you soon. It's going to be about kinematics, yeah, sorry that I couldn't, it's not really possible for me to show you what the cross product looks like. Again, when I get back, I'll explain in further detail, I guess, but this is an important concept, and please ask me if you have any questions. Thanks, and I'll communicate with you again soon.